So in this part of the lecture, we'll have a look at logistic regression. And this will give us another perspective on how linear models or separation models work with respect to actually introducing a probability space. And this is the foundation of every neural network that you later see that does class prediction. Because when you're predicting classes, just as we saw before, basically you want to yield a probability distribution, which means that you don't want to return just which class it probably is. But in order to actually do training on your neural network later, you want a class distribution for your given input data. And here we will lay down the foundations of which mathematical function we will need to use in order to produce a probability distribution instead of just one class value that you just spit out, and that's it. So what we need to define here is a setting of a feature vector again, and two classes. We're considering a binary scenario here, so spam and ham, for example, but basically anything that has two classes. And then we get our example data set D. And our task here, and we'll introduce a new learning task for that with a new algorithm and so on, is to use a logistic function. Some examples for binary classification problems. So in linear regression, what we basically did is we took our prediction function, so our model function, and just put in our weights multiplied onto our features x. And the form that we consider here, but this is also on the remarks slides, is including this 1 in case of x0, so we can also add some shifting value here. So what we get out of this is a linear model, basically just a straight line through this space, if this is a one-dimensional x. And now the question is, where would you put the boundary between spam and ham in this case? And a pretty straightforward way would be to just take it as 0. So everything that's below this line and also thus left of this line is supposed to be ham, and everything on the right is supposed to be spam. So this is how to predict things. What we need here is not only just predict a value for our model function, but also assign that value a meaning by defining a so-called threshold. And this threshold here is 0. Everything on our y-axis that's below 0 is ham, and everything above is spam. This is what you already know. But there can be problems. And these can, for example, because if some outliers are skewing this image. So basically, if I were to give this to you as a human, what you would do is still take the same threshold, 0. Still applies here and still would perfectly classify these examples. But in our linear regression that we used to introduce before, where we had certain ways of fitting this y, this wouldn't work out because it would shift actually the threshold that we have to define here and shift it to the right in a way that causes our examples left of this point here to be classified as ham. And what this means is that you get spam emails in your inbox, which you don't want. And this is a pretty tame example. You can also imagine other ML scenarios that involve a lot more risk than just reading an email. So we don't want this to happen, and especially we don't want this to happen out of such an avoidable reason, which is just this outlier being here on the right, where there's previously has been no doubt about how to classify this correctly. So the idea is now to define a different model function that actually allows us to ignore these outliers and basically only work within these bounds of binary classification. Because what we don't care or really care about is that here on the right, the model is so sure that this is a spam, because this is the highest value of y that we will observe. We don't care about that. What we care about is probabilities. So what we want to do is restrict the range of y between, in this case, 0 and 1, but depending on the definition of what we did for spam and ham, whether we did it with -1 and 1, then we would need another function. So we need to define some mathematical representation of spam and ham on this axis. But we really want to restrict the values of y. And a pretty straightforward way to do this is through such a function. So from school, you already know some functions that are restricted between 0 and 1, for example. So, or -1 and 1. So for example, the trigonometric function, sine and cosine, have a similar restriction. But here we want a function restricted between 0 and 1, it's between spam and ham. And what we use here is the sigmoid function. And this thing is pretty essential and basically part of every classification neural network that you will ever see. So this is important. So there are two parts coming in here. Still your linear predictor, that's basically your straight line coming through there. But this is plugged into your sigmoid function. So what you do is you first take the linear estimation, put it in here, and thus get a restriction onto the space between 0 and 1. And this is just the same, but that is replaced by WTX. So this is mathematically speaking how this works. From your feature space, you go into the interval between 0 and 1, but it's exclusive. So 0 and nor 1 will never be reached. And now the clue is that you can actually interpret this as a probability value. So in the lab, we will also check on some probabilities that we, some properties that we expect of probabilities, and we'll see that this function basically fulfills them, which is good because again we want class predictions. And in the very last lecture this semester, I think we will also consider a way to extend this to not only 2 classes but more classes. So we'll learn about a function that behaves similarly but is not one-dimensional but n-dimensional. So if we consider the probability that given a specific feature vector and weights for my model, the probability of obtaining class 1 or having class 1, that one is simply estimated through our sigma of WTX. And the inverse probability is computed as 1 minus that, because again, probabilities just sum up this and that. But what you need for this, of course, is to have each object either be class 0 or class 1. So no overlap, and especially no class 2 or something. Because otherwise this sum equals 1 wouldn't work. So here we have some examples. And what we can see here is that we build a threshold. And the threshold here in this case, I think, is 0.5. And everything that's right of it is classified as plus. Everything left of it is classified as minus, but what you really get is some probabilities for each point. So the probability that this here is class 0, and 0 is plus, I think. The probability that this is a plus is just 5%, as you can see here. But the probability of the same value, but annotated as a plus, of this being a plus, so probability of 1 under the condition of this feature vector, is 95%. And both values sum up to 100%. That's the idea of probabilities. And in reality, we wouldn't want this. We don't want the same features to be attributed to two different classes. But as you saw in the label noise example, this will happen in reality. And we can actually compute this and compute probabilities for both cases and actually say that this case here gives us a 67% chance that we have a spam, and 1 minus that value, or 100% minus that value of getting a not spam email. And in a classification scenario, we have to take this chance again and bring it back into a binary value. So, I mean, if you tell someone that you have a 33% chance of something being not spam, of course they would assume that it's probably the other case. But here what we need to do is introduce a threshold, which is now, in this case, 0.5. And everything above this we consider or classify as a spam, and everything else classify as a not spam. And now the question is how we can estimate our weights. And we do that again by optimizing probabilities. So before, what we did was we minimized the error in a linear model so that the model hopefully predicts the lowest, or the configuration with the lowest mean square error. And what we do here is we try to obtain the model weights with the maximum probability of, with the given weights, our data set being correct, so to speak. And we have another slide that actually tells us how to do this. And the thing that comes out there is a loss function that we want to minimize. And this will be, again, the foundation of a gradient descent algorithm that we'll have a look at in a minute. So just a small look over this remarks slide, but you can have a look at this on your own, is that we take our data set, and the probability that everything is correct basically boils down to a product of individual probabilities of a specific example with its feature vector and its class. So this, just without the weight, is the same form that we had in the previous slide set. But we now have a product here, and we can do some reformulation here in order to introduce a logarithm. And it goes on and on. But this basically boils down to another loss function. We'll have a look at this in the lab also, how this works. And when we minimize this loss function, what we actually do is we get the best possible model with respect to the probability of doing everything right. But we have a look at this in a minute. So here's another way to illustrate the whole thing, but with 2 dimensions for our feature vectors. So not only just in this direction, but also into depth. And what we basically do if we do linear regression is we put in a hyperplane, or a plane in this case, and everything that's above that plane, we define a threshold here. So this is the intersection of this imaginary plane here, separating our pluses and our minuses. And if we form a threshold, they never draw it here, but this edge here is the threshold. Everything that's above it is classified as plus, everything below classified as minus. But now in logistic regression, what we get is something restricted to the values between 0 and 1, so probabilities. And this works in multiple dimensions too, just because we take sigma of WTX. So the multiple dimensions fall out in this point, at this point here, because they're multiplied with the weights. And this is one-dimensional again. And this is how it looks if you write it out. And this is the separation boundary here that I was talking about. And yeah, if you want this, so this whole 3D setting really never happens in the sense that you don't have an explicit y-axis. Oftentimes you just have everything in the same plane because we don't know these values yet and annotate it. But this is basically the same demonstration. And you just take this boundary here and say everything that's right of it in this case. So everything with this arrow points is plus and everything else is minus. So now we want an algorithm, and we'll have in the lab, we'll have a further look at how this relates to our LMS algorithm, because the resemblance is quite close. Or especially also our BGD algorithm, a batch gradient descent algorithm. But this is a sigma variant. So we have a logistic regression algorithm with a logistic loss. So the loss function that you just saw is now used here in order to actually find the best performing model. And we have a further look, as I said, in the lab, but I want to quickly go over this here as well. So we start with some random weights, and we have a loop here. And in each loop iteration, what we do is we take our data set samples, we compute the model value y of x, and here what we have to do is put in our new model function, which now has this sigmoid function here, and this is how this is computed as. Then we compute our delta, and delta is the error that we get between our ground truth class and our currently estimated class with the current weights. And then we compute how to update our model weights. But we don't apply the update yet, but we accumulate this over the loop iteration, that just as we did with batch gradient descent. And we have eta again as a step size, and we have this remark here that says minus delta times x is the derivative of our loss with respect to w. But this is not obvious, because this is a whole nother function here. This loss function is a totally different function, and this y function is a totally different function. And coincidentally, the rest of the algorithm is the same. But in our lab, we'll actually compute this and actually see why this is the same and why the whole slide basically looks like the other slide, with the exception of that this is another loss and this is another model function. But if you were to design your own loss function here, for example, expect this to behave differently. So there you would really have to compute that loss again, compute the derivative of the loss again, or have a library like PyTorch, for example, do it for you. And this is what the deep learning people would do. They would never compute the derivative themselves by hand, but rather have the computer compute it. And then after we accumulated all the updates into our delta W, we apply it on our W, on our weights. And then in the next iteration of this outer loop, we work on the updated weights. And we do that until convergence again. And what we return is our model configuration, so our weights W. So here's the abstract representation of that. Evaluate your model, compute your residual, so the error in this case, compute the derivative, accumulate it, but actually keep in mind that there's this minus here is becoming a plus because the derivative points into the direction of the steepest ascent, but we want to go down. And here we have the parameter vector update, so for all scene samples, we apply one large update. All right. So let me quickly see how much we'll do today. Let's do a bit more. So this is again our ML stack here, which we also saw for our LMS scenario, but we'll also see it later for gradient descent itself. So the task is a binary classification. We have not yet generalized it to more classes. Our data, again, is a labeled data set. We need these binary labels to be assigned by a human, etc. Our hypothesis space is formed by our parameters W that define how the model behaves. And the model actually itself is defined by this logistic model. So our sigma of WTX. And our objective is to minimize this logistic loss. Regularization, we come to that later, but here in this scenario it's not happening. And our loss itself, as the loss function is written here. And I mean, yeah, there are other scenarios that can be improved by applying logistic regression and applying this trick of computing a probability instead of just a value that somehow represents the class. But I think they're not covered here. And here we see something that you probably find predictable from the lab, which is nonlinear decision boundaries. There we were at some point asked, or you were asked, to fit a parabola through a set of points. And the same idea can be applied here by taking a polynomial term, these squared values here, but still remain linear in the parameters. So the parameters W are again just multiplied WTX style onto these X values, but the X values themselves are modified into a form where they have the form 1, X1, X2, X1 squared, X2 squared, and so on. And so the higher order we get, the more complex functions we can actually fit. And you know such a representation from the representation of a circle, like the circle equation also uses these higher order, second order terms. And the same thing here again, we put it into our sigma, and we do a threshold, and we do the prediction, and we have our outer space where we have one class and our inner space where we have the other. And as I said, more complex polynomials give us more complex decision boundaries, but if we overdo it, if we do too many parameters, we run into overfitting, because then we can perfectly fit in between the space given by our data, but it might be that for unseen data, this perfect fit is just too much.